I think could be me. Just saying. So get this thing. Oops, wait. Do this. I'll do that one. Open Skype. Let's change slightly. So anyway, the that homework it was pretty good. I think everyone got like 90. The types of mixing, everybody got that, I think. And then it was pretty interesting what you guys said. Like the answers were pretty good. So there was a lot of different discussions about it. Anyway, it seemed to. I was pretty happy with the answers in that thing. Instead, so this I wanted you to give a list of steps on how to do it, and then some people did that. Basically, you had to use the word Fourier transform and the answer. Like after you grade them, and you realize how you're grading it, and you're just looking for this one word. Basically, you had to Fourier transform. I mean, there's more words you had to say, but if you included the word Fourier transform, so you have a time dependent, the relationship to get the frequency curves is the Fourier transform, which is why don't I say what that is? So if you have all right, let's go through or something. So focus thing. I don't think I said what a Fourier transform is, right? So focus. So it's basically if you have like say you have some signal, so you have some kind of signal that you get in, and say it's a function of time. In this case, it's our spectrum with the relaxation time of the thing. Like, but basically it could be any signal. So it could be a noise signal. So it could be just like something like that. Right? So, and then Fourier transform says you can break down anything. So anything can break down into a sum of like sines. A sine of like the two parameters, like time dot omega times 2 pi. So the angle is these two parameters that have inverse units, like time and frequency. Or it could be space and q. So you do a dot. Anyway, so and then times 2 pi gives a sine wave. So that means that if you're gonna in the time space, this thing's going to be a series of sine waves. So you have like different amplitude sine waves, like one like that kind of takes care of that thing. And maybe this one that goes like this, like take care of this part. So you have a whole number of these, so you're going to sum together. So you can sum together the sine waves. Each sine wave has an amplitude. So you have an amplitude. Each sine wave has a kind of a frequency. So versus frequency. If it broke down into just those two, then you'd have like a spike and a spike. Right, so that would be like, say it was an IR pattern, and it was a Fourier transform IR. So Fourier transform IR, you get a noise pattern like this in space by using a interferometer. So the incident beam, this sample, and then you have kind of a reflection. This thing's on a motor to position X of the incident beam, and it recombines with the incident. You get a noise pattern out of it. And then that noise pattern is composed of these sine waves. You decompose into the Fourier spectrum, which would be, you go like position X of that mirror, the moving around. And then there's another mirror here that the two waves combine incident in that one. And then, so that's a position space, and you convert it to frequency space or wave number. It's centimeter minus one, so wave number. Okay, and this should be like, so K or would be Q if it was scattering, right? So in scattering, you take a structure, like a random structure, like a polymer chain, and break it down into the Fourier components and give an amplitude versus Q. So the scattering patterns would be like real space and scattering space. Right. So the idea of the Fourier transform is just breaking down a signal into sine waves. And you plot the amplitude of sine waves versus the frequency. If it's time and frequency, or if it's a spatial distribution of something like the correlation function, the material is going to get put scattering on it. So it relates to things of inverse units, and it's going to use a sine wave to decompose the thing. Anyway, so that's kind of that's what's going on here. So he's taking this time dependent function and to get the frequency dependent. So number 7, to get the frequency dependent, he has to do the Fourier transform of it. So he had to use the word Fourier transform in there. Anyway, so and then
well as some of the different aspects of layering on other degrees like an MBA or things like that. So as was mentioned, I went to Lipscomb University. I got my MBA from Xavier. It was just a decision at the time. Xavier had a better part-time MBA program, so I chose Xavier over UC. And I have been in industry now for 17 years, all at Crane.
that's a long time. I'd hire him. Right. So anyway, so this thing everybody got, that intrinsic viscosity versus molecular weight, right? So that's the Mark-Hoenk equation. The prefactor for good solvent is 0.8. For theta solvent is 0.5, and he gets 0.7. So and then people talked about branching in this, and he says in the paper this demonstrate that it's not branched, which isn't, it's kind of not true, because it would be 0.8 if it was a linear chain and a good solvent. If it's a theta, so if it's a kind of theta chain and a theta solvent, then it's 0.5. So you can say, well, this solvent isn't exactly good, but you can also say if it's a branched chain, the dimension in the good solvent probably goes to 2.0 or something. It goes like a little bit larger dimension. That would make this Mark-Hoenk coefficient go from 0.8 to point something smaller than 8, like 0.7. That means it probably indicates they are branched chains and it's in a good solvent. Right. So anyway, the thing about that he says that it shows it's linear isn't exactly true. And also the high densities aren't linear, they're branched. They're branched, long chain branched. So anyway, that's one issue here with that. Nobody mentioned that, but I mean, I think it's a little bit deep into it, but and that our number C, and then D. So some people answered this really well with a series of steps, like how it, like explaining how a series of steps is the clearest way to do it. And then other people gave kind of wordy, long things. Some people gave kind of wrong answers. So I don't know. Actually, the answer to D is almost the same as B, but there's a little slight difference to it. But and kind of how you word it is how what the difference would be. And then E, this thing, I got, some people gave 1-line answers, some people gave 3 pages, right? So it's like, so again, it's like pretty interesting. It's kind of what I want, you know. So one line could be good enough, you know, it's the right line. And then there isn't really a clear answer to this. So basically, what did people say? Loaded, it dissolves So they said like it could be due, it didn't, like we said in class the other day, people just copied what we said in class. They didn't mix long enough. The longer you mix it, because it gets more viscous when you get more of the ultra high molecular weight, then it's going to take longer to mix it. So therefore you get a worse scenario for the blending, basically a kinetic answer to it. And then some people went over extensively about miscibility using the del parameter and stuff, which was kind of interesting. It was partly wrong, partly right. So, right. And then what else did people say? Then people like in class, we mentioned it could be like a phase diagram. And you could use that to get the chi parameter from this thing. So some people mentioned that. So there, yeah, but so that answer could, even though it's a short kind of thing, could be a pretty long answer if you wanted it to be. But I was pretty happy with the answers, the quiz, so I think it was okay. Any questions from you? All right, so we can get rid of that. So I'm up to, let's see. This guy is missing something. Oops, this is what I want. Oh, here, this is what I need. I never see the thing that's right in front of me. It's probably a sign of something, but. All right. 64 or something. Right, so last time I went through this thing. So about how you get the recent gyration, calculate it using a Polymer. So basically, it's a bunch of algebra. You substitute in L squared for the difference between the position N and M in the chain. And then you can end up with this kind of series expansion of the thing. And that thing you can rework into this thing. And then you can use this power series kind of math trick to get the answer n cubed over 6. And you plug in that double sum back into here. And then n cubed over n squared is n. And then you get end up with 1/6 n L squared in this thing, because it was a b squared here. So basically, that ends up giving you this thing, which means the rate gyration is smaller than the end-to-end distance of the chain by 1/square root of 6. So 2.45 times rate gyration gives it end-to-end distance. Kind of looks like 2 times the radius gives you the diameter, if you want to look at it that way. But this isn't a diameter, and this isn't a radius. Right? This is a moment of inertia, and this is some weird thing that has to do with the average separation distance for the end groups. And so the chain is actually larger than any of these numbers. I mean, the average chain is probably larger than those, both RG and our end-to-end distance. And they aren't really good exactly measures. And last time I said that the RG is subject to this problem, that's the 8th moment divided by the 6th moment. So that if you have polydispersed and with the Polymer chain, it's always going to be polydispersed, because you remember when we did the simulations, you had a chain like that, some chains like that, and you kind of sum those together to get this average chain, right? And then so basically, it's a polydispersed system, and with polydispersed, so if you take, you're going to get RG from scattering, which is e to the minus q squared RG squared over 3, which is going to be 1 minus q squared RG squared over 3. If you think of low q, which is where we use this, then a low q RG, then the prefactor to this thing is the number of electrons, which is the density times the volume, both the squared. These things are cubed squared, which is r to the 6, and then r2 gives you r to the 8. So that if you average this over a series of different sizes, you get the average r8. Then to normalize it, you normalize it by this prefactor, which you need to average R6. Would give you RG squared. And so the RG would be the square root of the 8th moment for the 6th moment. And the moments, if you have a distribution of things like this, would be some distribution like that. Then basically the mean would be kind of here. The R, average R is there. average R squared would be kind of like here. And then the average R8 is way out here. Right, so and R6 is something like that. So the numbers have nothing to do with kind of what you're looking for. So that ratio will give you something kind of nutty. That said, like if you have a monodispersed system, you have like number versus R, you just have one value, then all these moments are equal. And you have like average of R equals average of R squared equals average of R6 equals average of R8. And so if you have monodispersed, and RG is perfectly valid thing to use. But if you have polydispersed, it gets to be pretty goofy, like it isn't, it's going to be way too large of a number. And so anyway, so that's kind of important to know about RG and the way people, like you'll see in papers and people use RG and it's a polydispersed system and they're just using RG as the size, as the radius. So it's not the radius, and it's not going to reflect the size really. It's going to reflect the size. If a beach with sand on it and a couple of boulders, it's the size of the boulders. You know, so if you're measuring all the particle sizes in it. So it's like a useless number, essentially, unless you're interested in boulders. You know, so anyway, so that's one thing about RG, right? So there are other things to get the size from, especially for particles like sand, but that from scattering, you know, but anyway, so this is kind of like where you get RG, right? So if you plot and measure, say you have a Gaussian polymer chain, so it's going to have a power 2 log plot of intensity Q, power -2 to give you the two-dimensional, because it's NL squared is R squared. And at some point that if you're looking at that coil, at some point you reach a size that's large enough where you just see the coil. And at that point you see Gougnet's law. See this knee-like thing, which would be a bell-shaped curve in a linear plot about 0, right? So this is just a Gaussian function, right? So it's going to have that shape, and then you can pick off RG there. Another way to do that is to say 1 over this would be exponential to the plus, and then the expansion at low RQ would be 1 plus R squared Q squared over 3. So if you do 1 over the intensity, you get this linear function in Q squared. Right. So before they had computers, before you could do plots and do fits and show things like this, then you didn't have a way to fit things like that, right? So you had to linearize everything. So you see all these odd functions showing up coming from the 1950s when there were no computers, or 60s. Then the only way to analyze the data would be to like linearize the equation. Some you couldn't linearize. So you were kind of in trouble, but this equation you can linearize by doing this trick, right? So Bruno Zim was a guy, so after World War II, so this whole subject in here kind of goes back to World War II and Dubai and stuff. So anyway, Bruno Zim was a German Jew that fled Germany and came to New York, I think he was himself fled Germany because he was in the 60s. So, right. So anyway, he went and in Brooklyn was like New York was where everybody went. And Brooklyn Polytech became kind of like the center for science in the United States. So it was the MIT of the 1950s. And then MIT grew out of like radar and stuff. So actually World War II dumped a ton of money into MIT to develop radar. So there's like Lincoln Lab, they have their own national lab, their own Department of Energy, like weapons lab outside Boston, you know, which is kind of a secret place. And then so the money truck just kept dumping money there to develop these things for whatever reason. But before that, Brooklyn Polytech was the center because of the ethnic thing, because most of the top scientists in Germany, maybe half of them were Jewish. They all had to leave, right? So they all went to Brooklyn, and this Brooklyn Polytech, and it's still there, but it just isn't as prominent as it used to be, you know. So when Zim was there, Dubai kind of went through there. Who else was there? Zim was one of the most famous guys that was there, but all the famous Polymer scientists were there, right? So Zim was there. He developed this light scattering stuff. The other thing is that, like, my advisor at grad school, Dick Stein, worked with Zim, and then in his grade school class, there were like 3 Nobel laureates. I mean, they were not when they're in grade school, but afterwards they all moved on. It's basically Brooklyn became like kind of a center for like a generation of US scientists somehow. It's kind of a weird thing, like just the concentration. It shows you like when you have this kind of kicking people out of your country, you know, that like you're losing things. So, I mean, Germany would have had those 3, but they didn't because of that. So, and then Dubai also won the Nobel Prize for chemistry afterwards, but he stayed in Germany. And then it turns out, all right, so then they said like he was a Nazi sympathizer because he stayed. It turns out he was kind of an informant for the British intelligence. This came out like just maybe like 10 years ago. 15 years ago, they said he was a collaborator with the Nazis. And then 10 years ago, they realized that like, no, he wasn't. He was actually there as like a front man to get all the information about how the things like were the Germans developing nuclear bombs and stuff, or atom bombs at that time, right? So anyway, so he finally came to the US though, to Cornell. So anyway, so I mean, eventually they left Germany and took all his money, bought gold and made coat hangers out of it. So because they wouldn't let you leave Germany with money. You know? So basically he took gold coat hangers out. And luckily he got through with it, I guess. So anyway, some funny stories about him. But anyway, so Zim was one of the guys who came with the Zim plot, which is basically take this and get that. And then there's another part to the Zim story. So if you so in scattering, like I think I said this before, but basically if you have like a uniform system, right? So say like water, but here it's a polymer solution and you're at a Q value. So you have that curve like log I, log Q, -2 slope. That's the unity part. You have RG. Then there's this low end part, right? So at the low end part, you've zoomed out way beyond where you can see individual polymers, right? So you just have like a uniform system. So each dot is one of these polymer chains. That's a dot now, right? Because you've zoomed out so far, all you see is a dot, right? And this in solution. So what gives, the question is like, what gives rise to scattering? If it's a uniform system, it should be like clear, nothing should come out of it, right? So what gives rise to scattering is that those dots cluster up. Right? They're randomly moving around. So like the stars at night, some of them form like the Big Dipper, right? So it's a random phenomenon, but basically you can see that there's a shape to it, right? So basically KT is driving those things to form these things. And then when they get together, you get that problem with the osmotic pressure. You have dots on one side, no dots on the other side. Then the fluid like wants to dilute, so it wants to drive that pressure up, right? So it wants to dilute the dots. So it's driving them. Or, so that's answer 1. Answer 2 is it just, if there's no membrane there, the dots just disperse back. They go from cluster to disperse. The thing that drives them is that pressure, that osmotic pressure. Right, and pi is going to be a power series. So use the ideal gas law for that. So you PV. So rho is 1 over V, RT would be the ideal gas thing. And then you say, well, I'm going to add a series of rho squared. So divide this by RT, get rid of that. I'm going to have the second zero coefficient, which for a polymer is 1 minus 1/2 pi. Right, that thing. So basically you can do that. So that's what's driving this off. So it's a function of pi in concentration or in rho, right? Rho's of concentration. So basically if you want to know, it's like the change in pi with respect to concentration that's driving this thing. So it's like d pi d rho is what you want to know. So if you take that thing, you end up with like, and in polymers, you have to divide this by n because it's mass, and there's mass by n. The number of dots is the mass in the system divided by n, the mass of 1 dot, right? So the molecular weight of the chain is in there. It's got to be 1 over n, and plus this thing. The derivative is going to be like 1 over n, then the concentration, and then the zero coefficient, 1 minus 1/2 pi. by the Floyd thing. That's going to be the change in pressure that happens when it fluctuates in and out. And that's what's giving you your contrast. So that it ends up being that the intensity is 1 over that. This is called the osmotic compressibility. So it's osmotic pressure, and then how it changes with concentration. So it's like how if you're fluctuating the concentration, it's like a compressing the particles. They want to spring back. That's called the osmotic compressibility for whatever reason. Right. So 1 over that is the intensity. So if you have a large osmotic compressibility, then they don't want to cluster, then you get no scattering, right? Like say like how many of these dense areas you're going to get. If you have a higher osmotic compressibility, they'll want to disperse more. So 1 over that means that you get a smaller intensity for large compressibility where they're dispersing. If you have small compressibility, you get a lot of clustering because KT is driving them into the Big Dipper or whatever, or Orion or something. Right. So basically that's how the operation goes. So you want to get that term too, and that's the other part of the Zim equation. So you have this is in here. So here, all right. So that's this. So this is the other. This is the 1 over n. So this is B2. Oh, sorry. Yeah. All right. So this is the Guinier, 1 over the Guinier. So 1 over the intensity, and the intensity is proportional to concentrations. You have to remove that. In other words, if I put in twice as much stuff, I get twice as much signal, right? And so you have to say like intensity divided by concentration. 1 over that's concentration divided by intensity. This is the 1 over the Guinier's law expanded to where QRG is small. So you do the first 2 terms of the expansion would be like 1 plus x squared over 2 factorial set series. All right, so that's when Q and R are small, I use that one. And then this is the 1 over S would be the derivative of the osmotic pressure with concentration, osmotic compressibility. Right, so Zim just said, multiply those 2 together, and that works. And it does work as long as you're at low concentration and low Q. But there's no reason why you would multiply these 2 things together. It's just Zim just did that. Okay, so there's something to be said about, and then this Zim equation becomes like one of the fundamental equations to look at. And also one of the most mysterious equations because people don't understand where it came from. Like what is this thing? It's not really explained anyway. Right, so you just have the Zim plot. To linearize the data, then you're going to get the Zim plot, which is going to be this weird thing, concentration over the intensity versus, and then some other factor, like the contrast factor. And then it's going to be versus Q squared plus concentration times a constant. Q squared plus concentration times a constant. Yeah, so it's going to be this thing on the y-axis. And then to linearize it, you have 2 linear expressions. One's in Q squared, one's in phi. So you're going to have just add those 2 together. You have a double extrapolation. So you're going to have lines in constant Q where you can get chi from it. You're going to have lines in constant concentration where you can get Rg from it. And then if you take it to 0 concentration and 0 Q, you get the molecular weight, the weight average molecular weight, because everything's weighted by the weight concentration. Right, so you get the weight average constant. The osmotic pressure gives you the number average. This thing gives you a weight average. Right, so it ends up being a pretty weird plot. It's a double extrapolation. You have all the grid of lines going that way and grid of lines going that way, and then you can get 3 numbers from that: the chi parameter, the molecular weight, and the rate of gyration. So it's kind of nice. And it's accurate at low concentration and low Q. The problem is like it isn't really the right equation to describe this. But the right equation is the RPA equation, which I'll show you later on. It's a little bit more involved how to get it. So this is a totally winging it equation. Like you just basically you wanted to linearize the exponential, so you did that. Then you had this thing that was already linear in concentration, and they just multiply the 2 together. It's almost like, so you say like the scatter intensity would be the form factor, which would be like this number, and the structure factor, which has something to do with this number, multiplied by each other gives you the intensity. So it kind of looks like that, but that doesn't work in inverse. number one. And number two, it isn't true. That isn't how polymers work. Like, in other words, if you have fractal things that are intertwined with each other, they don't just, it doesn't work that way. So I'll show you how it actually works. It's more involved, right? So anyway, go back in time. So, and then last time I also went through, this business about this R vector. Now this is tricky. I don't want to do that. I do that. So I got to go here and go back there. So there's some vector R. So you have an incident beam. So the peaks are the sine wave of the beam, electric field wave that oscillates in space and in time. And then you're going to pick off a beam at the same wavelength, so the same grid. And to do that, you need to have points in space where the incident beam is in phase with the outgoing beam, meaning the moire fringe patterns here. So if you go to a small angle, the fringe patterns are separated by a big angle, a large angle is small. And so you have to have material located at those fringe patterns in order to get this outgoing beam. In other words, this beam comes in, excites the electrons, those give off waves like a rock in a pool of water, and then they're coherent, they're in phase when they're in phase if they're at these positions, right? Anyway, so that's kind of how the thing works. So you have to have material at that fringe pattern. So if it's a crystal, they have to be lined up along those fringe patterns to get a diffraction peak. So that's going to be a rare occurrence if you randomly throw in a diamond into the X-ray or a crystal, right? So basically you can grind up the diamond into a powder, and then some of them will have that condition, and then you can get the diffraction peak, but you've ruined the diamond. Or you could take the diamond and spin it around in space, right? So you do a rotation of the crystal, and sometimes it'll be in that condition and get the diffraction. Or you could come in with a multiple wavelengths. So you just don't monochromate your beam, and then you'll get kind of a starry night pattern out of this called a Lowy pattern. So basically some of the wavelengths will give rise to fringe patterns that are in the right position to give you the diffraction peak. So that's another way to do it. Right? So there's kind of like 3 ways to get diffraction to work for crystals. For polymers, it's not a problem because they're just gooey things all over the place. So it doesn't matter. Some of them will meet this Bragg condition. Right? So anyway, so that's kind of the operation. So you end up with a vector R, this vector R that's got a direction. The direction is that, so if there's an angle here of diffraction that's going out, then the angle of these fringe patterns is at half that angle. But so you have they talk about 2 theta, right? I versus 2 theta, that's kind of where the 2 theta comes. The first theta is kind of like where these things, fringes are, and 2 thetas where you're actually measuring it. Right? So in scattering, you talk about theta, so you end up with theta by 2. So 2 theta and diffraction is theta and scattering. So theta and scattering is theta by 2 in scattering. Diffraction and scattering. Just another twist to everything for whatever reason, a historic reason. Anyway, so we got that business. So this is the kind of scenario, looks like a mirror. That was your incoming beam, outgoing beam. This is at half the angle. So that would be the condition for specular or mirror reflection. So they call that a specular peak sometimes, or they call it a reflection. Like they call it diffraction peak or reflection because of that. It looks like the geometry of it's like reflection. Anyway, so that R is related to Q, 2 pi over Q Z R. So basically, as you scan the angle, you change the R, that vector changes. So as I scan angle, R gets small at high angle, gets large at small angle, and goes to infinity at 0 angle. So basically with X-rays, you can measure meters if you want. The problem is experimental, it isn't conceptual. It's like, because the main beam, so the main beam is going to be like 20,000 to 100,000 times brighter than this scattered beam, right? So you have this big footprint in the middle, and if you want to go to 0 angle, somehow like it's going to have kind of all kinds of, because the slits and things are going to make it not a perfect spot. Anyway, it still has a width, right? So you can't get to 0 angle. You can't measure meters with X-rays. but you can measure microns of X-rays. So you have a 1 angstrom beam going in, and you can measure 10,000 times larger than that with that beam, by that fact. But so it's like an inverse world. You can measure the large things, but you can't measure this. Like the smallest thing you can measure is lambda by 2. So the fringe patterns terminate at lambda by 2 in length. So there's a minimum size that you can measure. There's no maximum size. So it's like minimum to infinity type thing, right? So anyway, so we got that vector R, and that becomes like a theme. And you can think like R is 2 pi over Q, like they're Fourier equivalents. The R and the Q, the scattering vector, are equivalents. Q's defined as by the theta by 2 thing, 4 pi over lambda theta by 2. And you can figure out that expression from that fringe thing too, if you want. Like you can actually calculate it geometrically from that. But then, so we got that. So what happens if you want to get Guinier's law, say you have this blob thing, this black blob, and then you have the vector R, right? So if the 2 ends of the vector R are in the blob, then you get a scattering event that works. Okay. If one of the ends is in the blob and the other end isn't, you don't get a scattering event. Right. So say you're going to have these randomly distributed in the beam. So you can have them of all orientations, and then the conditions where you can get a scattering would be like those things summed together, right? Or you could take the vectors, so you can just kind of change the coordinate system and say, I'm going to base it on the vector. Instead of moving the particle around, I'm going to base it on the vector, and then I can just keep the vector fixed and then move the particle around it. So the average position of all the particles, if you do that for anything, you end up with that. Anything will end up being, if you wanted to say the probability of the 2 ends of the vector being in the particle, they'd end up being this kind of decaying 2D thing. Right. So it doesn't matter what it is. It can be a polymer, it can be a brick, it can be a chicken, anything. Then it'll always average to this kind of thing, which ends up being a Gaussian curve. Right, so that's the basis of Guinier's law. Like you have the Gaussian probability function, you Fourier transform that to get Q space, and then you get Guinier's law out of it. Right. So basically, Guinier's law is just saying you have a Gaussian like probability distribution that transforms into that same equation. The prefactor, again, is going to be like density times volume squared, so that it's going to be like R to the 6, and then R squared in here gives you the 8th thing. But all right, so anyway, there's that business. So what do we have here? Let's see. All right, so that's one kind of a this is called a binary correlation function. In other words, I'm talking about this R will always get binary because you're talking about here and here, 2 positions separated by a vector R. So you're going to consider the density, the probability if you're in the thing, if you're in the blob thing, and then what's the probability of the other end of that R being in the blob thing, right? So it's a double sum. Like the first sum is just the concentration of blobs. Like the probability of being in the blob is the concentration of blobs. The other one has to do with the size of the blob, right? So size and shape and whatever the blob is, right? So another thing you can do with blobs is this: you can take so say you had this scenario, you had that thing, right? And then you're saying, well, so I have these vectors I'm going to put into this thing, and then I reach the end of it, right? So I have an end area here. It's going to be a size R, and R varies. So R is 2 pi over Q. So as we change the angle, Q is 4 pi over lambda sine of the angle over 2. So Q is a reduced angle to get it into like a Bragg nomenclature. So you get R. And then when you get to this position, you kind of have a 50% chance, say, of having R count, right, when you're within that surface area. And the amount of that surface area is a surface, and then you have like the volume of things. So if you say what's going to be the probability, what call it here? So I'm just calling it another name, like gamma R. So you have 100% chance if it doesn't have a surface, And then the fact that you have a surface is going to reduce that 100% chance by this factor of the surface to the volume. And then divided by 4 because you didn't have 50% on this. So basically, S by R is like that area, and volume is the whole area. So you take in like the total. If S by R, if it was all surface, you get 0 correlation, and if it was if you zero surface areas, have an infinite particle, you got 100% correlation. In this thing, also you're saying like there's a direction to this, right? So with the Grenier thing, it's taken all the things to get that density function. And because you've randomized the things, there's no direction. But this thing, this surface scattering, there's direction. And that makes a difference because you can have plus R and you can have minus R, right? You have to have plus R for this thing to work. So you have to see a surface and say you're going away from the surface for this correlation function to work. So there's a barrier here between like random orientation and then not random orientation. So if you have not random orientation, then it's possible to have direction. Then you can get a surface to volume ratio. If you have random orientation, you can't get that. So you can see, all right, so this is going to, if you Fourier transform this thing, then you're going to get surface to volume ratio times q to the minus 4. That's called Porad's law. Joe's pronounced one. So that's surface scattering. That would be like if you had particles, look at log I versus log Q, and you're going to see this minus 4, and eventually that terminates in a Grenier. And so that would be your typical particle. This is the surface area, and the slope of that gives you the surface to volume ratio. And that's on a nano scale, so it gives you the same number that you get from gas absorption measurements. But that would be the other way to get particle surface areas, right? So, okay, the context here is that if you take this expansion of Grenier's law, 1 minus 3 r squared by 4 rg squared, then basically it doesn't have that power 1 term, right? There's no surface to it. So basically, this Grenier particle is a particle with no surface. No, oh, sorry. Yeah. Right. So you have this is a kind of equation you get for something that has a surface. It's got a linear r term because it has a direction. Like there's a direction away from the surface that you have to get it. This thing has no direction because you smeared out everything that was there, so it can't have a surface. So it can't have it doesn't have a linear r term. The expansion of this thing's 1 minus the x plus x squared by 2. And it's minus, so it would be plus and then minus x cubed by whatever, 3 factorial, 6. So anyway, so that's one thing you can say directly about a Grenier's law is it has no surface. So it gives you the size. So because everything smears out into a Gaussian, everything has a size, but it doesn't have a surface. So you need another approach to get the surface. In fact, it doesn't have any information about what's inside of it, right? So you only have this size out of this thing. Right? There's nothing about what it is. Everything's going to have the same features, right? So it's that business. So in terms of RG, I showed before how you get this 3/5 R thing. If you have a sphere, and you say it's 4 pi r squared for the surface of it. Right? So you say you're going to have spherical shells, and you're going to integrate that 4 pi r squared, and then multiply by r squared to get the average r squared. So that's like a weighting function for it. And then you have to normalize that by whatever the weighting integral, the weighting function is, which is 4 pi r squared, like dr. 4 pi cancels out. This is r to the 4, that gives you r to the 5 by 5. And this is r cubed by 3. So you get this 3/5. So rg squared is 3/5 of the radius of the integrals to r, 0 to r. to the radius of the sphere squared. So 3/5 r squared is the sphere one. And you can do the same thing for any kind of shape, any kind of simple shape you can think of. It's kind of a list of RGs you can get. All right, so you notice that here, so this is 3/5. So we have end-to-end distance by 6, and here's 3/5 r squared. So the RG is smaller than the end-to-end distance, but RG should be larger than the sphere diameter. Here, if I work this out right somehow. Don't exactly see how to do that, but basically 2 times the square root of 3/5, I guess, gives you something larger than 1. Is that right? RG and then distance by 6. Square root of 6. 3. This should work, but I can never tell. Yeah, it's 0.77 times 2 gives you 1.55. Right, so RG is going to be 1.55 times the diameter of a sphere. So if you take RG and the hydrodynamic radius, which would be this R, right? Hydrodynamic radius for a sphere is the sphere's radius. So that gives you a number bigger than 1, like 1.55. RG divided by hydrodynamic radius for a polymer gives you 1 by square root of 6, something much smaller than 1. So if you can use that as kind of a cutoff, RG by hydrodynamic radius, if it's smaller than 1, it's like a fractal thing, like a polymer. If it's larger than 1, it's a solid object. So say you had protein that was a native state or was unfolded. All you have to do is do a dynamic light scattering and stick it in an X-ray, get the radius gyration and the hydrodynamic radius, and you can tell which one it is. So that's kind of like a common thing people do. They take the ratio of the radius of gyration and hydrodynamic radius to get it, and then they'll talk about what the thing is. It's a little mysterious, and it's fraught with problems, like the polydispersity issue. Hydrodynamic radius, you don't even have the slightest idea what it's talking about because it's an equivalent sphere radius, whatever that is. So if you have a polymer that's draining, it could be small. If it's not draining, it could be large, right? So, but generally, people just accept the fact bigger than 1 is solid, smaller than 1 is like this fuse fractal thing, right? So anyway, so maybe you'll see that. I think we already, maybe it was hinted at in some other paper, but anyway, we'll see that again. All right, so that brings us to Debye and his problems with the Nazis, right? So in where is this link here? So this is kind of interesting. So let's see, I guess I have to display this. So this is the paper where he came up with this. So it's published in, so here, I can make that larger somehow. Anyway, maybe I can't. So it's published, technical report number 637. So this is like the Army. Technical report means the Army. Rubber Reserve Company was an Army base at Cornell University in World War II. So Debye was there for a number of years before that. Then April 9th, 1945. So May 9th, 1945 was when the Nazis surrendered. And then September 2nd, 1945 was when the Japanese surrendered. So it's exactly at the end of the war. Then the Army released all these secret documents. This is one of the secret documents because the Japanese, so most of the rubber was natural rubber at that time. In fact, all of it before World War II was natural rubber, and most of it was being raised in Malaysia, right? Even though the rubber tree, I think, is native to like Africa or something. So they imported and made these big plantations. That's where all the rubber was. And you needed rubber to have like airplanes or they couldn't land, things like that. Like you needed rubber for tires for Jeeps. Rubber was a strategic material in World War II, So anyway, so they set up a rubber institute. The purpose of it was to develop synthetic rubber, right? Butyl rubber and isoprene, right? So, or polybutadiene, I guess. Isoprene is natural rubber and butadiene. So they did that. So they built, so like there's huge plants in Ontario, like north of Detroit and Sarnia, like where the what is it, the Lake Superior empties into the whatever river that is. So there's huge plants there where they just made rubber in World War II, and it still makes rubber there. But so anyway, so this is all tied together, these giant factories and this research effort. And part of the research effort was to look at fundamental things about polymers, I guess. So this is one of the things, but everything that had anything to do with that, because they were afraid that somebody like the Germans could get it and then somehow win the whatever by making synthetic rubber. So people were pretty tight-lipped about things, I guess, but it's kind of interesting. Like you see this and it's like not in a journal. This is like a really important paper for polymers. It's not in a journal, it's just in a technical report that's like dumped out just at the end of the war. But he does the derivation in here. Also, it's not even like printed like in a journal, it's just typewritten, on a typewriter. So I think in those days, like the equations, you somehow, this would be literally you'd cut out these symbols that were already printed and form them together by hand, like you'd glue this together into a proof and they like take a picture of it and make an offset print from it. It's like this is I literally typewritten on a typewriter. And then sometimes you can see how the lines aren't really lines, they're like typed, hand typed, so anyway, it's kind of interesting. But anyway, so he goes through how to do that derivation. So the derivation of that is basically, I'm not going to go through it, but it's in that paper. So basically it's similar. He ends up with the correlation function. Let's see. So the correlation function for polymer chain is going to, del means yes or no. So yes is 1, no is 0. And then if your vector r, that r thing, matches this difference Rn minus Rn, which is like the same thing we had like kind of somewhere here, Rn, and then, I mean, this is the Rg derivation thing. So, and then if that's yes, then you say yes, and then you get a correlation. And then you add it in, normal. Same thing as we did for Rg with the 1/2n squared, so like a 2n squared. Right. So it's the same as the Rg calculation. Then you plug that in. Anyway, so you do a transform of that, and you basically get this function. This function, which is the scattering function for a coil by Debye. So next time I'll kind of go through a little bit about how you can analyze that equation and get some sense out of it. So, all right, so I'm going to put there. I'll dig up a paper. Yeah.
So I heard like a lot of polymers are the grades, like sometimes it like build up like in our like
Yeah.
system and stuff. Is there any difference between like natural rubber versus like synthetic rubber? And
Natural
how
rubber
that
degrades. Yeah,
Okay.
it does degrade.
So the synthetic rubber that has like a harder time.
It doesn't degrade.
Oh.
It's more than a hard time. Yeah, totally. So butadiene doesn't degrade. Then sp. So a lot of the tread compounds like butadiene, styrene, block copolymer, anionic block. Neither one of those degrade.
Okay.
But the original tires do, like the isoprene ones. That's why, I don't know, if you had a bicycle or something and it was out in the sun and the tires fall apart eventually. They turn into goo. I don't know if you've had that experience, but I have. Like they'll just bubble up, they destroy themselves, like they get consumed somehow. Yeah, I probably have one in my garage somewhere that's like that. It's just chewed up, so they degrade. So there are rubbers that degrade. So anyway, yeah, so people are looking at matching that. Anyway, there's things people are doing with that, like block copolymers with a degradable and non-degradable and things like that. So butadiene isn't one of them. And that's the main kind of material used. So